Topic 8.4, strong and weak acids and bases. This diagram here is actually something that you'll look at in more detail in IB Chem 2. This is a higher level topic. If you look at the acids, you can see the strength of the acids increase as you go up, and the conjugate base of those acids increases as you go down. So what we say is that the conjugate base of a strong acid is relatively weak, whereas the conjugate base of a weak acid is relatively strong. Again, something you'll learn more about in IB Chem 2. Strong versus concentrated. In English, the words strong and concentrated are often used interchangeably. In chemistry, they have very precise meanings. Strong means to completely ionizes or dissociates into ions. So it simply means it breaks apart. Like sodium hydroxide, the sodium and the hydroxide ions would break apart. It's a strong base. It completely ionizes, breaks apart. Or the term dissociate also just means to break apart. Concentrated is a high number of moles of solute per liter of solution. So you can have a strong acid be very concentrated, or you could have a weak acid be very, very concentrated. So they mean different things. Weak only slightly ionizes or dissociates into ions. Dilute, a low number of moles of solute per liter of solution. So you could have a strong acid, like hydrochloric acid is a very strong acid. Well, you could put a drop of that strong acid into a swimming pool. Well, it's going to be very, very dilute, and still it's a strong acid. Where conversely, acetic acid, which is a weak acid, you could put gallons and gallons and gallons into the swimming pool, and it would be more concentrated, but it's still a weak acid. So the difference between those two terms. Strong, weak, concentrated, dilute mean different things. Strong acids. Any monoprotic acid that 100% ionizes or dissociates. So meaning, and HA is our generic representation of an acid where A is the anion. So if you have a strong acid, you put it into water, it 100% ionizes. Every single molecule that goes into the water breaks it apart to form hydrogen ions and the anion. Now, monoprotic is the case for strong acids, diprotic and triprotic. Though you can have a strong acid be di or triprotic, it's only the first hydrogen that is released 100%. But don't worry about that. You're only going to be asked about monoprotic acids. Therefore, the strong acid concentration would be the same as the hydrogen ion concentration. So imagine if the acid was 1 molar, well, that means you put it into in solution, you're going to have 1 mole of hydrogen ion. So it's going to be 1 molar. So whatever the concentration is of the acid, that's exactly the same as the concentration of the hydrogen ion. If you have 1,000 molecules of the acid, you'll have 1,000 hydrogen ions. And the pH can be directly determined from the concentration of the acid. So the pH is equal to the negative logarithm of the concentration of the strong acid, because the strong acid concentration is the same thing as the hydrogen ion. We'll do a practice problem on that in just a second. Okay, these are the common strong acids you need to know. Hydrochloric acid, hydrobromic acid, hydroiodic acid. Of course, those are all halogens, chlorine, bromine, and iodine. Not fluorine, but those three. Nitric acid, perchloric acid, and sulfuric acid. Now, sulfuric acid is a diprotic acid. However, only 1 proton 100% ionizes. So when you put the H2SO4 into water, it 100% ionizes, but if the ions are the hydrogen ion and the bisulfate ion. The bisulfate ion itself is a weak acid. It only partially ionizes. This is more FYI. You don't need to worry about any special calculation for it. I'm not going to give you sulfuric acid. That's something that is a little bit of a higher level problem. Okay, let's do some practice. Calculate the pH of a solution made by dissolving 4.50 grams of nitric acid in enough water to make 1,200 milliliters of solution. Now, what's important here is that it is a monoprotic strong acid, and that's the only thing that I will be giving you. It's much more complicated if it wasn't monoprotic or if it wasn't a strong acid. So to do this, just like what we talked about earlier, the concentration of the hydrogen ion is going to be equal to the concentration of the strong acid itself. So we have all that we need to calculate the concentration of the acid. Of course, concentration is moles divided by liters, and we're given grams and milliliters. So we need to convert grams into moles and milliliters into liters. Now this is revisiting what you learned last spring. Our very last unit online was concentration, so this will look a little bit familiar, I hope. So the first thing we'll do is convert grams into moles. The molar mass of nitric acid is 63.02 grams. And then we need to convert milliliters into liters. There's 1,000 milliliters in a liter. So just let dimensional analysis help you along. Milliliters cancel out. And that will give us the concentration of the hydrogen ion being 0.0595. Now, all we need to do now is plug that into our pH calculation, our pH equation. So the pH is a negative logarithm of the 0.0595, or 1.23. So the trick here is simply calculating the concentration of the acid, and if it's a strong acid, we can plug that into the pH equation rather than hydrogen ions, it's the concentration of the strong acid. Next, weak acids. Any acid that does not completely ionize. Common weak acids: hydrofluoric acid, hydrocyanic acid, nitrous acid, and acetic acid. Now, a little bit about acetic acid. That is its common name. But as you'll learn when we get to our unit on organic chemistry, it is an organic acid. It contains what's called the carboxyl group. This is a preview. You don't copy it down, but this is not something that you'll be tested on or anything. It contains what's called the carboxyl group. You will be tested on it when we get to our unit on organic chemistry, though. And this is the carboxyl group. The COOH is a abbreviated way of writing this. And so what we have here is a carbon that has a double bonded oxygen and an OH. That's called the hydroxyl group that we'll get to. The name for the organic acid is ethanoic acid. And so this is the name that you'll hear, that if you were to read your textbook or in the IB world, they would never use the common name acetic acid. They would always say ethanoic acid. In your homework, there's an assignment that refers to ethanoic acid, and so it's this.
For weak acids, ionization is partial, reversible, and can be considered reactant favored. So they do not dissociate very much at all. Let me give you a couple of real examples. Hydrochloric acid is a strong acid. So strong acids, as we've discussed, 100% ionizes. Whatever the strong acid is, every single molecule, when you put it into water, will ionize, forming hydrogen ions. That is not the case for weak acids. Nitrous acid is a weak acid, not to be confused with nitric acid, which is strong. It only partially ionizes. Specifically, only 1.7% of all the molecules of hydrogen nitrite that you put into water will ionize. So most of the molecule remains intact. And this is how you would denote that. In your homework, you're asked at one point to distinguish between a strong and a weak acid as far as ionization. So strong acids, 100% ionize. Weak acids will have reversible arrows, and it'll be favored towards the reactant side. You don't need to worry about the numbers.
Note, calculating pH for weak acids is an HL topic, so you don't need to worry about it. And in fact, in order to solve it, you need to use the quadratic formula. Though there is an estimated method that you'll be taught in IB Chem 2, rather than using the quadratic formula. Okay, strong bases. Any Arrhenius base that 100% ionizes dissociates. Now remember, an Arrhenius base contains the hydroxide ion. So this would not be a Bronsted-Lowry, not necessarily a Bronsted-Lowry base. So it 100% ionizes, so this is just like a strong acid. So rather than 100% ionizes to form hydrogen ions, it 100% ionizes to form hydroxide ions. So therefore, the concentration of the base is equal to the concentration of the hydroxide ion. Same logic as we used for strong acids. And the pOH can be directly determined from the concentration of the base. So our equation for pOH can now be, rather than the negative logarithm of the hydroxide ion concentration, it's the negative logarithm of the strong base concentration. So they're interchangeable. Common strong bases. Group 1 and Group 2 hydroxides. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. And then in Group 2, there's just 3, calcium, strontium, and barium hydroxides. So those are all strong acids. They will all 100% ionize. Now notice for Group 2, if I had 1 mole of calcium hydroxide, I would have 2 moles of hydroxide. However, I don't think I'm going to give you any of those problems. Common weak bases, ammonia, just kind of file that away. Ammonia is a weak base. It's almost always the only base that we deal with in standard level. Now there's also amines. Amines are NH2. When NH2 is bonded to an organic molecule, it's referred to as an amine, and it can be a proton acceptor to form NH3 with a positive charge. This is something you'll see when we get to our unit on organic chemistry. But for our purposes, it'll be just ammonia will be the only weak base that we would ever talk about. Practice. Calculate the pH of a solution made by dissolving 2 grams of potassium hydroxide in enough water to make 750 milliliters of solution. So just like with the strong acids, we will convert, we will calculate the concentration of the base, the potassium hydroxide, which will be exactly the same as the concentration of the hydroxide ion. So we have 2 grams of potassium hydroxide in 750 milliliters of water. So we need to convert the grams to moles and the milliliters to liters. And so this gives us the hydroxide ion concentration of 0.0475. Now before you go running off to calculate the pH, remember that is not the hydrogen ion concentration, that is the hydroxide ion concentration. So when we plug that into our negative logarithm equation, it will give us pOH. In this case, pOH of 1.32. To calculate the pH that you're asked for, we would need to subtract that from 14. So the pOH is 12.68. And a good thing to just remember to reflect back upon what you're given and what your answer is. Here we're asked to calculate the pH of a strong base. And so if you wrote down that the answer was 1.32, you weren't thinking, because remember, acids will have a pH of less than 7, bases will have a pH greater than 7. So it wouldn't make sense for a strong base to have a pH of 1.32. So, kind of always stop and think whether your answer makes sense.
Watch a video, this is a few minutes long, on distinguishing between strong and weak acids and bases. After this, we will summarize.
This is MSJ Chem. In this video, I'll be looking at how to distinguish between strong and weak acids and bases. So in this video, I'll be looking at 3 methods to distinguish between weak and strong acids and bases. The first is to measure the electrical conductivity, and this can be used to distinguish between weak and strong acids and bases. The second is react with an active metal or metal carbonate. This method can only be used to distinguish between weak and strong acids. This is because bases do not react with active metals or metal carbonates. And the final method is to measure the pH of the solution, and this can be used to distinguish between weak and strong acids and bases. So we'll start by looking at electrical conductivity. On the left, we have a 1 mole per decimeter cube solution of a weak acid, which is ethanoic acid. On the right, we have a 1 mole per decimeter cube solution of a strong acid, which is hydrochloric acid. If we look at the brightness of the bulbs, we can see that the bulb on the right is brighter than the bulb on the left. This means that the solution on the right, the strong acid, has a higher electrical conductivity than the solution on the left, which is a weak acid. The reason for this is that strong acids and bases have a higher concentration of mobile ions in solution. Therefore, they have higher electrical conductivity than weak acids and bases of equal concentration. So to summarize, strong acids and bases have higher electrical conductivity than weak acids and bases. Note that in each of these methods, we are comparing strong and weak acids and bases of equal concentration. Next, we look at rates of reaction. Here we can see two sets of reactions. In the first set of reactions, we have magnesium reacting with hydrochloric acid and magnesium reacting with ethanoic acid. In the second set of reactions, we have calcium carbonate reacting with hydrochloric acid and calcium carbonate reacting with ethanoic acid. So in both sets of reactions, the fastest reaction will be with a strong acid. So strong acids have a faster rate of reaction than weak acids of equal concentration because they have a higher concentration of hydrogen ions in solution. Next, we look at pH. In this table, we have 1 mole per decimeter cube solutions of strong and weak acids and bases. A 1 mole per decimeter cube solution of ethanoic acid will have a pH of approximately 2.4. For hydrochloric acid, the pH will be 0. For ammonia, the pH will be approximately 11.6. And for sodium hydroxide, 14. So if we compare strong and weak acids of equal concentration, strong acids have a lower pH than weak acids. And if we compare strong and weak bases of equal concentration, strong bases have a higher pH than weak bases. So to summarize, strong acids have lower pH values than weak acids of equal concentration. And strong bases have higher pH values than weak bases of equal concentration. So let's end with a summary. Note that in all of these methods, we're comparing weak and strong acids and bases of equal concentration. Starting with electrical conductivity, strong acids and strong bases have higher electrical conductivity than weak acids and bases. Next, rate of reaction with active metals and metal carbonates. Strong acids will have faster rates of reaction than weak acids. And finally, we have pH. For a strong acid, the pH will be low. For a weak acid, it will be higher than a strong acid. For a strong base, the pH will be high, but for a weak base, the pH will be lower than a strong base.
How to distinguish between equimolar, strong, and weak acids and bases. Equimolar simply means that they have the same concentration. So the only differences between them is the nature of the acid or base itself, not the concentration. Okay, so let's look at acids going from weak down to strong. Of course, we know that all acids are going to have a pH of less than 7, but when you get down to around 0 to 2, that's the realm of strong acids. Electrical conductivity increases as you go from a weak acid to a stronger acid. Reaction rate increases. And the heat released in a reaction, neutralization or reactions with metals, would increase. All reactions involving an acid with either a neutralization reaction with a base or with a metal are exothermic, so they give off heat. So if you were to, say, put magnesium metal into a 1 molar solution of acetic acid and 1 molar solution of hydrochloric acid, the temperature change in the hydrochloric acid would be much greater. The temperature would rise much greater because it's a strong acid. Compare with bases going from weak to strong. Of
course, the pH for bases is going to be greater than 7 and increase from there. When you get to around 12 to 14, that's the realm of strong bases. Electrical conductivity increases as we go from a weak to a strong base. The reaction rate increases from weak to strong. And the heat released would also, just like an acid, be much greater for a strong base than a weak base. However, notice that we don't include metals here. Metals do not react with bases, or not, at least not in the same manner. Okay, so all of this, the key idea behind all of this is ways that we can distinguish between a strong and a weak acid and base. And that is it, the end of notes.